Okay, so this is the first video for the course E227 solid mechanics. So let's just get started with this. So basically, the mechanics of solid is a part of continuum mechanics, and continuum mechanics is basically the branch which deals with, which basically considers that matter is basically fluid and like a continuous fluid. And so basically, we in solid mechanics we try to find the mathematical equations which describe the physical laws. Like if I stretch a rod, then I need a mathematical equation. Like I can have a mathematical equation which describes the physical laws, and like these equations are called the field equations. So basically, let's just take an example of continuum mechanics and where it is defined. So we know that we define density as limit delta v tends to zero, delta m upon delta v, right? So we know that if I consider a small, if I consider, let me consider a small box. So like if the box is comparable to the size of a molecule, then like suppose if a molecule is inside the box, then the density at that point would be higher. But if the molecule is outside the box, then that density would be here. So like at an atomic scale, the density actually varies and it's not a constant as such. And there's also a thing called microcontinuum, and this microcontinuum also, like basically the box is like very large compared to the size of molecule, not very large but it's large, so that like individual molecules do have a slight effect on the density. And classical continuum is basically the place where the volume which we are considering contains a lot of molecules and is a lot bigger than the size of a molecule. So basically, due to the random motion of molecules, there is basically no effect on the density. So it's almost constant in this case. Basically, yeah. So basically, in the range of volume, delta V tends to let me just yeah. Basically in a volume range, as delta V is basically less than very very less than the critical volume, then we do not expect continuum mechanics to hold. And like matter is assumed continuous when we have this like our volume which we are considering is a lot larger than the critical volume or the V star. And when like we assume that continuum mechanics holds that matter is continuous, then properties are also continuous point functions of uh, continuous point functions of, like I mean, like if I take an example of density, then at a particular point I have its specific value. Like our density is a scalar field, like so at a point I can define rho of xyz. So like basically at any point xyz, if I put in the coordinates, I can have a function which gives me the density of that point. So basically it's a continuous, and like that function of density is a continuous point function. And also there we can basically define two types of equations: the balance equations are basically true for all materials, and constitutive equations, they might not be true for all materials. Like if I take Hooke's law, then I know that stress is equals to stress by strain is equals to Young's modulus, right? So Young's modulus is basically not like a fixed constant. So it's not the balance equation. It's a constitutive equation because it has a parameter Young's modulus, which is not, which varies for different materials. Like we don't have the same equation for each and every material, basically. Yeah. Yeah. So basically, this was the initial part of the motivation of solid mechanics. So basically we can now move on to the mathematical part of it, the mathematical equations and the mathematical preliminaries which we might need for this course. So yeah, so let's get started. So the first basic mathematical preliminary that could be said in this course is the which could be said as the most important thing in this course is the index notation or the Dirac notation. So basically, index notation is like I can write an aij as a subscript ij, or I can also write as aij as a capital, as a superscript, and I can also write this as aij. So all these three things are basically they represent the same thing. So basically this is it. So like there's just also summation notation. So like I mean, in usually we use the sigma notation to denote summation, right? So like if I write EIXI, then and write the sigma symbol, then it will basically mean a1 x1 plus a2 x2 plus a3 x. So just to basically have like to remove the like to have a convenient notation, there is this Einstein summation notation, which is like if you write AIXI, that basically implies that you are writing it as a sum. Like if you write AIXI, that basically means you are summing over all I. So like you mean A1 x1 plus A2 x2 plus A3 x3 till AN xn, you are basically summing this up if you write AIXI. And here like the index I appears twice, so like basically any index which appears twice implies that you have to sum over that index. So obviously summation does not apply to numbered indexes. So like if I write a2 x2, then it does not mean anything. It just basically means the term a2 x2. It does not mean that I would sum over a2 x2. If I instead I write aj xj, then that would mean I would have to again write sum over all AIXI, right? And also there is this thing that repeated indexes may be represented by any other letter. So like if I write AIXI, then that would also be equal to AJXJ. Like I can basically replace I with J. So yeah. So also if there is this thing called dummy index and free index. So if there is a doubled index, suppose if I write AIJXJ. Suppose if I write AIJXJ. So in this, j is repeated twice. So basically, which implies that I would sum over j. But I is a free index, so basically I would not sum over I for in this case. So in this case, I would be my free index, and j would be my dummy index because I'm summing over that j basically. So yes, this is it. And so let's now move on further into the mathematical details. So there's also this thing called as the Kronecker delta function. So the Kronecker delta function is basically denoted by delta ij. So it has two indexes I and j. So basically it means 0 that when I is not equals to j, and it means 1 when I equals to j. So there are basically some properties that delta ij xj is equals to xi. So basically delta ij xj means that you would sum over j. So delta 1, sorry, delta I 1, just a second. So delta 1, that j would be 1 and x1, and the other part would be plus delta I2 x2. So basically you would sum over all j, right? So basically in the end you would get like when j is equals to I, you this xj would be converted into xi, and that into delta ii would be 1, of course when I equals to j. So basically that would be xi, and also delta ii is equals to n. So delta ii, which means that there are two index, right? I is repeated twice. So basically I would do delta 1 1 plus delta 2 2 plus up to delta nn, and that would be equals to that would obviously basically equals to n in that case. So now there's this important thing for delta notation, that I have this thing called the dot product. So if I have any two unit vectors ei, then their dot product would be equal to the delta ij. So if I have a basis ei, e1, e2, and e3, so if I take any random ei and ej, so their dot product would be denoted by delta ij. And also I can also use the Dirac notation or the Einstein notation to represent vectors. So if I want to represent a vector A, I can write this as AIEI, and I can also write this as BIEI basically. Like, so obviously this would imply that is A1 epsilon 1 cap plus A2 epsilon 2 cap, and so on basically. And I can also basically then prove this or then just write this as a dot product. So yes, obviously this would be the easy dot product. So I can write a dot b as AIEI plus AIEI dot BJEJ. So that would, like, I mean, they are all just basically multiplication. So basically I can write this as AIBJ times EI cap dot EJ cap, and we know that EI cap dot EJ cap is delta IJ. So this is AIBJ delta IJ, and like that would be obviously when I equals to j, then delta IJ would be 1, otherwise it would be 0. So basically it just sums down to AIBI, which was obviously the dot product which we consider for two vectors like A1 B1 plus A2 B2 plus A3 B3, and so on. Yes, so basically this is the AIBJ, and there's also this thing called the permutation symbol. Just there's also this thing called the permutation symbol, which basically means that this its value is 1 when I, j, and k form an even permutation, and its value is -1 when I, j, and k form an odd permutation. So basically, I, j, k may form an odd and even permutation, which means is that if I take 1, 2, and 3, I equals to 1, I equals to j equals to 2, and k equals to 3. So basically, they are all in ascending order, and they form like 1, 2, and 3. Basically, when I arrange them in ascending order. So if I take I is equals to 2, j is equals to 3, and k equals to 1, I can basically also arrange this as 1, 2, and 3 in even number of tries. Like if I basically consider I replace this I 1 and 3, so basically I'll be 2, 3, 1. And then if I do it again, I would get 1, 2, and 3. So basically that's an even number of tries. That's two tries. So basically that's an even permutation. So it gets 1. So like I mean, obviously this is kind of uh, how can I say it? This is kind of like cumbersome to do. So basically, we can just basically write like yeah. Here we have this example. So 3, 2, and 1. I can basically convert it into 3 2 and 1. I can replace so 3, 1, 2. And so basically this we need like three odd permutations to do it. So like epsilon ijk for 3, 2, 1 would be -1. And like there's just basically a notation and like notation kind of thing, so we don't need to like memorize its values and such. We can just basically use this, like we if we kind of know its properties, we can basically apply it for any other further calculations which we required for this. Yeah. So basically, the next is basically we can there's this nice property of this, as we use the like delta notation, like the direct delta function to represent the dot product. We can also use this permutation symbol to denote cross product. So like if I take two vectors, a is equals to ai, and the other vector b equals to bii, then my vector a cross b would be epsilon ijk, ak, aj, bk, and ei cap. So basically, I would need three indices, right? I, j, and k. So the jth one would be aj, the kth one would be bk, and the ith one would be ei cap. So basically, I have three I, j, and k indices, right? So basically, I can basically sum over. So like if I take I equals to 1, then I would get the eith component of for this. Like I equals to 1, then I would have to sum over basically j and k. So like j and k, I would have to like this, since there are two j's, right? Here aj and epsilon j and aj, and there is also one k, epsilon k and bk. So basically I would have to do two summations over j and k, all j and k, and to basically get the value the component eith component, the eventh component for this. So in that case also we can basically this prove that b cross a is equals to epsilon I kj, bk, and aj. So basically what we can do is we can replace k and j with this and use the use the property of permutation symbol that we are basically replacing it once. So like one is an odd permutation, so epsilon ijk would be like minus epsilon ikj, and in that case we would have b cross a is equals to minus of a cross b. That it's that simple as that. So basically it just we are discussing its properties, and like we would like once we know the properties, we can just basically use this to prove any number of like simple permutation. And like in this case we can there's also the scalar product. So scalar product also we can write in terms of this. So like c vector dot a cross b vector. So we know that a cross b vector is epsilon ijk, aj, bk, and ei cap, right? So ei cap, and like I can take denote c vector by cr er cap, this cr and er cap. So basically this is cr is a constant, and epsilon ijk and aj, bk is also a constant. And this is a like direct delta notation. Like I mean, this since we are taking the dot product of two basis vector er and ei, so this is delta ir, and this is cr, epsilon ijk, and ajbk. These are all constant as such. So in the end, like basically after like computation, we have this value epsilon ijk is equals to aj, bk, and ci for this question. Like I mean basically since it is delta ri, right? So like if I r equals to I, that in that case delta ri would be 1. So basically instead of cr we are just replacing it as ci, and again it's just epsilon ijk would still be here, and aj, bk, and ci. So that's it basically for this, for all the like notations which we consider. So there's also this thing called tensors as such, which is like basically as we studied in our linear algebra course, a second order tensor is a mapping from a vector to a vector. So basically, if I have a v vector, I want to go to another vector u, then basically this tensor is a transformation from v vector to like if I apply this tensor on this vector v vector, then it would just transform me to a u vector. So it's basically a linear transformation. So a tensor is a second order tensor, as specific, is basically a matrix and which transforms a vector to another vector basically. So yeah, this is all the like the mathematical preliminaries that we needed for this course, the basic mathematical preliminaries. So in the next video, we can basically check the other mathematical preliminaries for this, and we can basically then move on to defining chain and other functions as such for this.